Yesterday actually I have discussed the standard methodology of heat equation, right? Now actually we are going to solve some of the basic problems that are required as part of heat equation. So the heat equation solution, the general solution, what we have discussed is, that is, good evening. So Liju, are you facing the issue? Are you facing the video issue? Can you refresh yourself? Is it fine now? Okay, great. So now actually, so this heat equation, the general solution, so at any instant the temperature is nothing but, so u of x comma t is given by, so e power minus c square p square t, then c1 sin px plus c2 cos px. So this is the general solution of the heat equation, and this is what is the most preferred solution out of the three possible solutions that we have discussed, right? Now let us note down one problem. So this will cover all the aspects of the heat equation. So if you are able to solve this problem, that is sufficient for the preparation purpose. Note down this problem. An insulated rod of length L, an insulated rod of length L has its ends A and B maintained at, has its ends A and B maintained at 0 degree centigrade and 100 degree centigrade. And at 100 degree centigrade, respectively, until steady state conditions prevail. Until steady state conditions prevail. If B is suddenly reduced to 0 degree centigrade and maintained at 0 degree centigrade, if B is suddenly reduced to 100 degrees to 0 degree centigrade and maintained at 0 degree centigrade, find the temperature at a distance x from A at time t. Find the temperature at a distance x from A at time t. So this is the problem statement, and the same problem statement is extended further. So first actually let us solve till this extent, then actually we can see how we can extend this further. Now if you notice in this particular problem statement, what happened is, just see this, there is a rod like this, and then this rod is maintained 0 degree centigrade here and 100 degree centigrade here. Then the steady state conditions prevail. That means they kept these temperatures for a long time. Obviously, the temperature is distributed across this particular rod, and this part is maintained at 0 degree centigrade and this part is maintained at 100 degree centigrade. Suppose if I draw the graph of this particular temperature distribution under the steady state condition, so this is going to be, so this is the X and this is the temperature. So this will be linearly increased from 0 to 100 degree centigrade. So this part is, this is length, or actually I will put this as, yeah. So this is the distribution, right? So this is at 100 degree centigrade and this is at 0 degree centigrade. This is how the temperature is distributed, right? Over the length of L. So because this length is L, so this point is L. Now, what is the steady state distribution at any displacement X? What is the steady state distribution? Let us say this is the temperature, right? Or actually I call this as U. Then U of X given by 100x by L. Correct or not? Got it or not? The slope of this is 100 height and this is L. So this is theta. So tan theta is equal to 100 by L. So the slope of this is 100 by L. So y is equal to mx is the standard format. So in this standard format, so u is nothing but given by slope 100 by L into x. So at any displacement x, this is how you will be able to find out the steady state temperature. Got it? Got this or not? Is this understood? No, Avinash? So what is your question? It is just actually the initial condition. Actually, if I correlate the same problem statement to the wave equation, so here actually in the wave equation, so he will be giving an equation which is the initial displacement which is given to the string, right? In case of wave equation, that actually usually maybe sin pi x by L or maybe mu into x into L minus x. So yesterday actually we have solved one problem based on that. That initial displacement here in the wave, in the heat equation, he didn't mention that initial displacement. Rather than that, before starting the problem statement itself, what he said was this is maintained at 0 degree centigrade and this is maintained at 100 degree centigrade. And then like that actually he kept for one day, let us say. Then after that what he did was suddenly he immersed this 100 degree centigrade into water so that it maintains 0 degree centigrade and he kept it like this. Now this is also 0 degree centigrade now and this is also 0 degree centigrade, and this is how actually he tried maintaining the temperature. Then over some time actually this entire rod here is going to get 0 degree centigrade after certain time. Now in between, so he will be asking what is the temperature distribution, how it is going to be temperature distribution across the entire length of the rod and at any time t. So if t is equal to infinite, obviously it has to come out to be 0. Got it? So that's what he asked us. Now earlier actually in the wave equation he used to give the initial condition, but actually now we have derived the initial condition based on the description whatever he have given. Got it? Okay, great. So this is the temperature distribution. So initially at x comma 0, this is the temperature distribution, which is nothing but u of x comma 0. This is 100x by L, which is one of the boundary condition for us. Okay. Then what happens is, now actually let us see how it is going to distribute with the help of the wave equation. Now the general wave equation solution is coming out to be this one. Now the boundary conditions after t is equal to 0. So that is after t equal to 0, what happens? So this term, that is at point A, u of 0 comma t is maintained at 0, and at B, u of L comma t also is maintained at 0 after t plus. So at t is equal to 0, this is how the distribution it is. Got it? So these are the two other boundary conditions actually what we have gotten. Now if you try to find out the values here, this is u of x comma t is equal to e power minus c square p square t and then c1 sin px plus c2 cos px. Now in this equation, if you substitute u of 0 comma t. So u of 0 comma t is maintained at 0 degree centigrade, e power minus c square p square t, and then so this is at 0 plus c2 cos px. So it implies this is going to be 0, which implies c2 equal to 0. Now after substituting c2 equal to 0, then u of x comma t is going to be e power minus c square p square t getting multiplied by c1 sin px. Now substitute the second boundary condition, that is u of L comma t is again 0, that is u of L comma t. So this is e power minus c square p square t into c1 sin px equal to 0. So it implies sin px equal to 0, that is the only possible method. So then PL. So PL is equal to n pi, because the general solution of sin is n pi. So from this P is equal to n pi by L. So we have got the value of P. Now so this is u of x comma t is given as e power minus c square, now n pi by L whole square into t into c1 sin n pi by L times x. So this is the solution. Now this is, we have introduced something called n here. Now again actually we have to deal with the Fourier series format. So note down till this point, then actually we are going to bring the Fourier series format for it. Done? Is it done? Okay. Then now actually we will be using the last boundary condition, that is we have got the solution in the form of u of x comma t is equal to e power minus c square n pi by L whole square times t, and then c1 sin n pi by L into x. So this value we have got. Then so the initial boundary condition u of x comma 0 is 100x by L. So that is u of x comma 0 is equal to 100x by L, and then this value is equal to, so sigma Bn. So this C1 actually you can replace as Bn, because we have introduced n, as I said earlier. So if the distribution is this format, then actually you can express as if like it is a Fourier half-range series. So Bn, so at t equal to 0, this is going to be 1, and then this is going to be sin n pi x by L. So this is n is equal to 1 to infinite. So this is Fourier half-range sine series. So if this is the series, then Bn value you will be able to find out. Bn is equal to 2 by L times of integral 0 to L. So this equation, that is 100x by L into sin n pi x by L into dx. So this is how actually we will be finding out the Bn value. This Bn is going to be, so this is 200 divided by L square integral 0 to L. So x times of sin n pi x by L into dx. Now this is going to be 200 by L square. So this you can apply the UV or the by parts formula. This is U into the integral of sine is, so minus psi cos n pi x by L divided by n pi by L minus derivative of x is 1 and the integral of this is, so minus cos integral. So integral cos is sine. So minus cos, sine n pi x by L divided by n pi by L whole square. So this is how actually you are going to get it. Now substitute the upper limit as L and the lower limit as 0. Then this value is going to be 200 by L square so 200 by L square, and then so this value will be, so if I substitute x is equal to L, so L times of minus cos n pi divided by n pi by L plus, so sin n pi is going to be 0 minus, so 0 if you substitute it, this part is 0 and this part is also 0. So this is how you are going to get it. This is, so this is n pi by L, so L square will cancel, 200 by n pi into, so minus cos n pi, so minus cos n pi is minus 1 and whole power n plus 1 because 1 minus is extra. So 200 by n pi times minus 1 whole power n plus 1. Let me check the answer. Yeah, that's correct. Got it? So this is the Bn value. Once you got this Bn value, you can replace this Bn value in the original equation. The final solution is going to be u of x comma t is equal to e power minus c square n square pi square by L square into t into minus 1 whole power n plus 1 into 200 divided by n pi times sine of n pi x by L. So this is the distribution at any time and at any displacement for the temperature. This is the final solution. Got it? Understood? Or do you have any questions on this? Okay. Now actually the same problem statement we can extend to a little tougher level. So if you understand this one, I am going to erase it and then we will extend this. Can I erase? So in the same problem statement, there is an extension to this, that makes you a little complicated. Note down that extension, that is, solve the same problem if the change consists of raising the temperature of A to 20 degrees centigrade and reducing that of B to 80 degrees centigrade. Solve the same problem if the change consists of raising the temperature of A to 20 degrees centigrade and reducing the temperature of B to 80 degrees centigrade. So if this is the change, earlier actually this is already at 0 degrees centigrade and this is suddenly immersed into the water from 100 degrees centigrade to 0 degrees centigrade, it came out. And then this is how actually we will be maintained. Now the change, rather than maintaining this to 0 degrees centigrade, what he did was he raised the temperature of this to 20 degrees centigrade. Then he reduced the temperature of this to 80 degrees centigrade. Then he maintained that way. Now how it is going to distribute after some time? So that is the problem statement now. How we can solve this? How we are going to solve this? Any idea how we can solve this? Obviously the initial conditions are going to change, right? So just changing the initial conditions will not give an appropriate solution for us. Why? Because the complexity that is involved in this particular problem statement is little more than what we have discussed till now. Why? Because see this, earlier actually this boundary condition is 0 and this boundary condition is also 0. Then only we will be able to simplify the equation by avoiding the arbitrary constants. But now this is not 0, this is going to be 20 and this is going to be 80. Now if without having the the 0 boundary conditions, it is very tough to solve the unknown variables there, right? That's where the complexity lies. Now because of that reason, what we are going to do is the total solution, as if like it is the any normal ordinary differential equation, the solution u of x comma t is divided into the steady state solution plus the transient solution. So this is the steady state solution and then the transient solution. So this is, we will be dividing in this particular format. So the steady state solution is straightforward and easy because as if like it is a linear distribution. Suppose if I keep this temperature at 20 degrees centigrade and if I keep this temperature at 80 degrees centigrade and I wait for 1 day, then actually what happens? The same temperature is maintained 20 here and 80 here and it will be linearly distributing between these two. Got it or not? So that's what is nothing but the steady state solution. Now if I draw the graph of this, then this is going to be like this. Now actually this is the over length of L. Then it starts with 20 degrees centigrade and then finally it leads to 80 degrees centigrade. So this is 20 degrees centigrade and it leads to 80 degrees centigrade in this particular format, right? Now the slope of this particular curve is nothing but 80 minus 20 divided by L. So that is y is equal to mx plus c format now. Y is equal to mx plus c format distribution. So this is the steady state solution. So why we are calling earlier one as the initial part and now actually we are saying it is the steady state solution. Why? Because earlier actually before we make temperature 0, this is how the temperature is distributed in a linear format as if like 100 by L times of x. But now this is after the experiment is done. That means he made the changes and waited for 1 day. That means it is after the experiment. So this is how it is going to be distributed. This distribution we call as the steady state solution. So this steady state solution you can keep it as, that is y is equal to m is 80 minus 20 divided by L into x plus the c value is the initial y intercept which is 20. So this is y is equal to 60x by L plus 20. So this is u of x. This is the steady state solution. Got it? Now the transient solution actually we have to identify the limits. So by making this change, then the transient solution you can find out. So ut of x comma t, you will be able to find out u of x comma t minus us of x. So this is how actually you will be able to find out the initial conditions for this. Why are we taking as a temperature distribution as a linear combination? Because we are saying it is independent of T and there will be a linear distribution of the temperature from here to here. That's the reason actually we take as a straight line, because this is what is the steady state solution. But the transient solution will definitely differ. That will be a completely a non-linear equation. And the differential equation, whatever we are going to solve, is for the transient solution, not for the steady state solution. This is as if like it is a particular integral for us. Now, just imagine practically maintain this temperature 20 degrees centigrade and maintain this temperature at 80 degrees centigrade, and this is a rod. Then actually, don't you think that the temperature is distributed in this particular format? This is after 1 day, it's not the tangent change. We maintained the temperature 20 here and 80 here and waited for 1 day. Then what happens? Is it not the correct solution? Deepak? Yeah, so that's the reason actually the steady state solution actually it will be a linear solution for us because this is a line, not a plane. So that's the reason actually we kept it this way. So if it is a 3D or 2D, then actually it won't be a straight line, obviously, right? The distribution depends on the shape of the plane. This is a line. Yeah, okay. Now actually the transient solution part actually we have to identify ut of x comma t. Now ut of x comma t minus us of x. Now this value, the initial conditions, that is at x is equal to 0, the boundary condition, and x is equal to L, the boundary conditions actually will be deriving for t is equal to 0. So this is ut of 0 comma t is equal to u of 0 comma t minus us of 0. So this value is going to be the temperature at 0, that is at x is equal to 0, what is going to be the transient temperature? So that is u of 0 comma t, that is initially this is at 20 degrees centigrade, and then us of 0, that is again 20 degrees centigrade. So this is going to be, yeah, so this is going to be 0 degrees centigrade. Got it? Got it or not? Then similarly, exactly in the similar manner, on the right hand side also, the temperature that is going to be maintained at the other side, so that is ut of L comma t is given as u of L comma t minus us of L, that is at x is equal to L. So this is going to be 80 minus 80, this is again 0. Now this is how actually for transient solutions we were able to identify the 0 initial conditions so that I can simplify my equation to a solvable manner. Got it or not? So this is how actually we brought the initial conditions to the 0. Here? Yeah. Now actually exactly in the similar manner, so that is at 0, that is u of x comma 0. So that is at time 0. So u of x comma 0, so this is going to be 100x by L, that is the initial distribution, minus, so that is the steady state solution at any time t, so this is 60x by L plus 20. Got it? So this is the initial condition for us. So this initial condition is going to be 100 minus 60 is 40x by L minus 20. So this is u of x comma 0. So now actually the roles that are taken by this is the transient solution at 0 comma t. So this actually the same boundary condition as if like in the previous case for the transient solution. Earlier it should be the complete solution. Now it is for the transient solution. This is 0 initial and this is 0 initial. The temperature distribution for the initial condition purpose of the transient solution, this is how actually is interpreted. Got it? Now the procedure is exactly same. So till this point actually you need to understand. Any questions on this? Any questions on this? Is this understood? Now, so once you will be able to find out, yeah, so the transient solution, so based on these conditions, so now actually the general solution of ut of x comma t is interpreted as e power minus c square p square t into C1 sin Px plus C2 cos Px. So this is how actually you will take it, and at t equal to 0, the initial conditions. So you will be substituting 0 comma t and L comma t and x comma 0. These three conditions, if you put it in this particular format, you are going to get the steady state solution with the help of the Fourier series equation, where the function is taken as 40x by L minus 20. Clear? Got it? Or do you have any questions on this? Got it? I need response. If you have any doubts, you can tell me. Okay. So now actually based on this understanding, so that is so if you substitute the initial conditions for this, what you are going to get it is ut of x comma t value, you are going to get it as bn times of sigma n is equal to 1 to infinity bn times of sin e power minus c square t square into t. So this is n pi by L whole square times t, and then sin n pi x by L. Now for this actually, so if we substitute the condition of, that is u of x comma 0, ut of x comma 0 is going to be 40x by L minus 20 is equal to sigma n is equal to 1 to infinite. This is going to be 1 because t equal to 0. And then bn times of sin n pi x by L. Sin n pi x by. Okay, anyway. So I think so you asked me to explain after erasing. Anyway, I am going to come back. Let us see this. So this is 40x by L minus 20. Now here, for this actually, this is again Fourier half range series. Half range series, sine series. Now this value, bn value, you will be able to find out. Bn is equal to 2 by L times of integral 0 to L and 40x by L minus 20 into sin n pi x by L dx. So this actually we need to be doing the integration 2 by L times of 40x by L minus 20. So derivative of this is minus cos n pi x by L divided by n pi by L minus so derivative of this is 40 by L and integral of this is minus of minus, this will be plus, derivative integral of cos is sin n pi x by L divided by n pi by L whole square. Now the upper limit is L and the lower limit is 0. So once you substitute the limits, you are going to get the value of bn as bn value you are going to get it as minus 40 by n pi into 1 plus cos n pi. You are going to get this way. Right? So if you are getting this way, then this is minus 40 by n pi and this is 1 plus minus 1 whole power n. Now for any odd number, this is going to be 0, and for any even number, this is going to be 2a. So if I take n is equal to 2m, then this is minus 40 divided by 2m pi into 2. So this 2 will cancel. Then this is going to be minus 40 by m pi. Got it? Minus 40 by m pi. Now you just replace this value in the transient solution part of it. That is going to be ut of x comma t. You are going to get it as the transient solution. That is sigma m equal to 1 to infinite minus part t by m pi into e power minus c square, n is 2, that is minus 4 c square m square pi square by l square into t sine of, so 2 m pi x by l. So that is the transient solution. Got it? Now, once you get this one, then the final solution, what you can write it is, so then the final solution is going to be, so u of x comma t is nothing but the final solution, which is nothing but steady state solution plus the transient solution. Now if you notice, the transient solution is dependent both time and the place, but the steady state solution which depends only on the place, not on the time, obviously, right? Got it or not? Yeah, Samrin. So let me explain this tangent and steady state concept. See this. So here actually in the previous problem, because here also 0 degree centigrade and here also 0 degree centigrade, that's exactly the reason we were able to easily simplify the solution in a simpler format, right? So this is a little complicated solution. For this you have to identify C1 value, C2 value and P value. For that actually the procedure takes long time, or actually almost it is impossible to find out these conditions because we have taken certain assumptions there. Now here actually the thing is no zero initials are coming because actually this temperature is raised to 20 degrees centigrade and this temperature is fallen down to 80 degrees centigrade from 100 degrees centigrade. Now in such case, so we have divided the solution into two different parts, that is the transient solution and the steady state solution. The transient solution we mean that is the changes that are happening, so when the changes are still running, right? So that is the transient solution where so the changes are still happening with respect to time. But in case of steady state solution, what happens is it is independent of time, that depends only on the space coordinates. That means the temperature that you are going to see it here, it is, this is dependent only on the length. It doesn't depend on the time, right? So if it is not dependent on the time, it just depends on the space itself, then we call that as the steady state solution. Steady state means no change with respect to time. That means the change happened and wait for 1 day or 2 days, then actually you are not going to see any change in that particular phenomena with respect to time. Got it? So that state we call as the steady state solution. That means if you notice, based on the physical conditions itself, we can make out the temperature distribution is linear in case of steady state, which is completely independent of time and just dependent on from where actually you are looking, that is the space coordinate x. So that's why the steady state solution is simply a function of x alone. But the transient solution is nothing but as and when the change happened, then actually it is going to be in trauma state, right? So the trauma state will continue for certain time, right? So till the oscillations that are die down. Now that the region we call as the transient region. That transient region solution plus steady state solution, so all together will give the complete solution for us. That's what we have written it here. This is the transient solution and this is the steady state solution. Understood? Somebody? Now based on this understanding, this is the steady state solution we already know based on the initial conditions itself, and this is the transient solution for which actually why we made this particular format is you wanted to bring in the zero initial condition at this stage and the other stage so that you can solve this equation very easily. For that actually this format is assumed. Then actually u of x comma t minus ut of minus us of x is nothing but the transient solution. So from there actually, so ut of x comma t we brought into the form of u of x comma t minus us of x. So this format actually we brought in, and then based on this actually the initial conditions we made it to 0, because this is also 20 and this is also 20 and this is also 80 and this is also 80. These are the two different initial conditions which are 0 for us. So that is how actually you applied exactly the same procedure to apply so that you can get this particular solution, that is the transient solution, which is coming out to be this one. Got it? Now the final solution is, that is u of x comma t value, actually you wanted to write it. For that, the steady state solution we have brought in, that is 60x by L plus 20 is the steady state solution. And then the next one is minus 40 by pi. That is the transient solution. And sigma m is equal to 1 to infinity, that is 1 by m times of sine 2m pi x by L into e power minus 4 c square m square pi square divided by L square into t. So this is the final solution. So this is the steady state part and this is the transient part. So transient will be more complicated because lot of changes that are going to happen during that particular stage. So any system, if there is certain level of oscillations, whatever may be the kind of oscillation, maybe heat oscillations, maybe a string oscillations, maybe a wave oscillations, or any kind of thing you can take it, any control system analysis you want to take it. So there will be certain oscillations during the transient region. Those oscillations are given by this particular equation for us. Got it? So this is the transient solution part of it and this is the steady state solution part of it. So together will give the complete solution at any instant. Got it? So this is, if you notice clearly, this is e power minus 4 c square m square pi square by L square into t. So here actually if you notice, as t keeps on increases, let us say t becomes infinite, then this is going to be e power minus infinity, then this entire part will become 0. Then we have only the steady state solution part of it. But at t is equal to 0 plus, that is immediately after 0 plus, then this value will be a finite value. Then the kind of behavior that will be shown by this transient part is going to be quite predominant on this entire solution of it. Got it or not? Clear? Any questions on this? Any questions? So this is about the heat equation. So this is the complete analysis. You may expect questions only based on this kind of scenarios. If you have any questions, you can let me know. Or else actually, so in the next class, I am going to deal with the Laplace equation. After that, we will be having only two classes. That is one on method of characteristics, another is the canonical forms. Here, that will be the last of our sessions. Any questions, you can tell me now. Got it? Okay. Yeah. So that's all for today. Thank you. Good night.